Alright guys, so welcome. We are going to be doing our recorded lectures now. So I hope you're all at home and safe and everything like that. I did have the option to video record the lectures for you, but turns out my camera does not zoom enough for me to get you a decent shot of the lecture slide screen. So we're going to do this via audio. So each slide should have an audio recording attached to it, so you just play that, or you can just read through the slides yourself. And I hope you are all at home, comfy, and ready to talk about fossils and their place in time and nature, right? All right. All right, guys, so we're going to kind of start our journey talking about taphonomy and, more importantly, paleontology, right? So, over the course of the next couple weeks or the next couple recorded lectures, we're going to talk about kind of the human fossil record and what different fossils we've found so far and what actually differentiates the genus Homo, which is what we are members of, from the rest of kind of the members of our family tree. But before we get into all of that, it's kind of important to understand or at least contextualize what exactly is a fossil and how do we look at fossils. So remember that fossils are the remains of organisms that have been chemically turned into rock, right? And remember that taphonomy, or when a paleontologist does a taphonomic study, they're studying what happens to an organism after they die, right? What happens to the remains? Are the remains scavenged, right? Are they washed away in a river, or do they kind of become a fossil, right? So we'll kind of discuss the different kinds of fossilization and kind of the uniqueness of what it is to be a fossil, right? So remember last time when we looked at this particular image, I asked you guys, what the heck is this and what's going on here? And, we eventually determined that this is actually a sea creature, right? This is a whale. And what's important about this particular image is if you look down a little bit south of the tail there, you're going to see a little circular bone. That is what is called an acetabulum, right? That bone actually is the remnants of the whale's pelvis, right? Because whales used to be creatures that walked on land. So here right now we can see in the fossil record or on this fossil itself, kind of evolutionary leftovers, right? That pelvis is still there, or pieces of that pelvis are still, contained within the whale's anatomy, but they're not being used for the same purpose anymore. So just shows you that in terms of evolution, that anatomy becomes shifted over time when you have changes in locomotion like this. One of the more fundamental principles that we see in the early days of paleontology comes from a gentleman named William Smith, and he developed something called the principle of faunal succession, right? And really, this is a very simple concept stating that all fossils that are found in the same layer, our same geologic layer, are contemporaneous with one another, right? So in essence, what we're saying is that those, when you find a bunch of fossils in the same layer, right, all those creatures lived around the same time as one another, right? So this is how we can use fossil layer beds to kind of relatively date the fossil in which you're looking at, right? We have two broad categories of fossils. We're going to talk about fossils in terms of categories and then in terms of types, right? So there are categories of fossils like your volcanic fossils, either the non-flattened fossils that become essentially encased in volcanic rock, much like your Laetoli footprints from Ethiopia that you can see on the left here. And then you also have sedimentary fossils, which are formed when the creature dies, and basically sediments build up on top of that dead creature over time and essentially turn it into a fossil, right? So there are slight differences in how the fossilization occurs, right? Volcanic fossilization, of course, we all know the classic example of Pompeii, which I believe the next slide is going to show you, or in a couple slides, we're going to show you a picture of one of those kind of Pompeii casts that were created via volcanic fossilization, right? But in terms of commonness, most of what we find is sedimentary fossils in terms of what's out there in the actual field. When we examine human fossilization, or our ancient ancestors, essentially the hominids from Africa, there are two main areas that we see fossilization occur. We see fossils being found in the East African Middle Awash region in Ethiopia, right, in Kenya. We also see fossils being found in cave systems in South Africa, places like Sterkfontein, um, Rising Star Cave, and others. And the kind of question originally was, how do these fossils get into these caves? We don't really see much habitation. And we actually see when we look at some of these fossils, there's actually evidence that these individuals were killed by large predatory cats. So what we think may have been happening is something they refer to as the leopard hypothesis, right? These large predatory cats would hunt and grab a tiny little ancient human, right? Whether it's an Australopithecine afarensis, right, or a younger Ardipithecus, then take them, drag them up into a tree, and crunch on them and drop their bones. And as those bones laid on the earth, right, in South Africa, you have a lot of karstic geology and geography, right? So that means there's a lot of very soft stone that can be eroded away with water in the bedrock. So essentially, caves form very easily. So as to, erosion occurs over time and caves form up underneath in the bedrock, those bones that were laying on the surface end up falling down into those caves, and that's how we get those ancient human fossil deposits in those caves in South Africa. Here you can see some puncture marks that were made by the canines of a large predatory cat. So this was definitely an individual that was gnawed on and probably killed by this cat and then eaten later. So this is just showing you evidence of how we think those bones came into those caves, right? It's important to note that when we look at fossilization, right, why don't we find, lots and lots of creatures, billions of creatures over the course of the evolutionary history of this planet have died, right? So why don't we have billions upon billions of fossils? Well, many, many dead things don't fossilize, right? In fact, very, very few of our early hominid fossils exist. So we think this is due to things like predators, scavengers, decomposition that happens too quickly, and really what you need for fossilization to occur is very, very slowed decomposition, right? And what helps that a lot is having an anoxic environment, right? Which is really just a fancy way of saying that it's an oxygen that lacks, or an environment that lacks oxygen, right? So what you need is to find a way in which the remains are not exposed to oxygen or scavenging by scavengers or predators, or being washed away and eroded away using water, right? So you need to find a way in order for those remains to remain undisturbed and not degraded by oxygen. And that's really why fossilization is so rare in the animal kingdom after a creature dies. So I won't point out where the Megalodon tooth is. I know we did this in class, but this just kind of goes to show you in a lot of cases when we are out in the field, or when paleontologists are out in the field, we're not digging up full skeletons, right? It's actually very rare to find a full skeleton. When we get at later on in the recorded lectures, you're going to see that a lot of the ancient human fossils, some of these Ardipithecus pieces, some of these Australopithecines that we have, are very fragmentary, right? And that's because in a lot of cases what we find are tiny little pieces, right? They fossilize, you get a tiny little chunk, and it's really kind of working from those tiny little pieces that you find and doing these reconstructions, right? It sometimes takes years upon years for a paleontologist to complete a reconstruction based on these tiny little fragments. It's important to understand the limitations that the fossil record presents us, right? Because in essence, we're really only working with a snapshot of life in the past and not a complete snapshot, right? So recognition of this limitation is critical when you're interpreting the fossil record, right? An example that we use is we talked in primate paleontology or primate evolution about that Fayum area in Egypt, right? Well, we see that the fossilization there, or that fossils stop at 29 million years ago. Does that mean that all of those apes and monkeys and animals that were living there decided to move? They were no longer living there? No, it just simply means that the conditions which made fossilization conducive simply changed, right? They're no longer producing fossils at that site because environmental conditions have changed, right? So we need to realize this when we're looking at the fossil record. We're not looking at migratory patterns of creatures in the past, right? What we're looking at is, well, this is just when the environment was conducive for fossil making. So, like at Fayum, we kind of run into the same quandrum when we look at early hominid fossils, right? Why do most early hominid fossils date to only about 4 million years ago or later, right? We know that we diverged from chimpanzees around that 7 to 9 million year mark. What was happening in between there? Were there no hominids earlier than 4 million years ago, right? Or were there earlier hominids somewhere else that we just simply haven't found yet? Most likely, right, the environment was just not conducive to fossil formation, right? So the best areas of preservation that we have are in Eastern and Southern Africa after 4 million years ago. And we'll kind of look at this, and I'll give you dates. I won't test you on the dates, but I will kind of give you a timeline of how this works, right? So beyond that 4 million year mark is a big gray area. That's why we have to use that molecular clock or that DNA evidence to try and figure out where we diverged from chimpanzees. We're just missing the fossils from that 3 to 4 million year period. When looking at the past, it's important to take everything into perspective, right? Or more importantly, take time into perspective. Long expanses of times that paleontologists deal with, things like millions upon billions of years, are kind of difficult for people to conceive of, right? Because we only live as, single creatures less than a century, right? So it's really kind of hard for us to even understand how long 1,000 years is and how much things can change and how much morphological change can occur in those vast expanses of time, right? So it's necessary to place fossils in time and space to fully understand their significance and how they relate, more importantly, to where we are today as creatures, and more importantly, how those fossils relate to one another in the time scale. In essence, there are three established eras and times in Earth's history, right? So we have the Paleozoic era, the Mesozoic era, and the Cenozoic era, right? Changes to the Earth's crust, that continent, Pangaea, and the formation of oceans occurred as mammalian, primate, and human evolution was occurring, right? So what I want you to kind of understand, or when we look at the next couple slides here, I want you to just get into the notion that, well, all this geologic change was occurring at the same time that mammals were evolving, at the same time that primates were evolving and moving around the world, right? They weren't working with a globe as we have it today, right? They're working with something that's a little bit different, right? Land was a little bit oriented differently back then. And we have to kind of take that into account when we're looking at how creatures were distributed in the ancient past. So some of the types of fossilization that we're going to look at is this notion of unaltered preservation, right? This is when it occurs so quickly that you don't have much degradation in the specimen itself, right? We're going to look at amber fossils. We're going to look at ash field fossils. We'll look at asphalt fossils, as well as ice fossils, which is kind of a misnomer because ice fossils are actually not fossils. They are just very well preserved. We'll look at lake sediment fossils as well as peat bog fossils. When looking at some of our unaltered preservation type fossils, we have these amber fossils, right? The amber itself is a semi-liquid sap that takes millions of years to harden. In essence, it goes through three stages, right? It starts out as sap coming from the tree. And then as it begins to kind of harden into a semi-hard substance, it turns into a substance called copal. And then once it is introduced to water, and this is kind of interesting, I don't know the specific biochemistry behind it, but some chemical reaction occurs in the copal that hardens it even further once it's introduced to water, and that turns it into amber, right? So it does not, amber itself does not harden in the forest, right? Only in marine environments. And what it does is it causes perfect preservation. It's one of the few instances of perfect preservation. All organs and even the DNA, for the most part, is intact, right? As a matter of fact, the picture that we have featured here to the right shows, not only does it show a tiny little ant there up in the corner, but it also shows the tail of a dinosaur that had feathers, right? So it's kind of interesting. So this I throw in here because I wanted to show you guys, copal is actually a resource that's used in Central America and has been used by humans for thousands of years. It's in essence an incense, right? It actually has a very, very strong piney smell to it. And the ancient Maya in the Yucatan Peninsula of Mexico, what they used to do is they would create these large things called incensarios, basically large ceramic incense burners. You can see one featured here to the right. And what they would do is the incense or the copal, they would get it nice and red hot and put it down inside of the incensario, and then the smoke would come up through the eyes, through the nose. For this particular specimen we have here, you can see that the nostrils are open, so the smoke would come directly out of the nostrils. And it also come out of the top, kind of billowing like a big volcano. And they did that to kind of increase the mysticism surrounding their kind of ritual practices. Another type of preservation fossil that we see is these ash fields, right? The organism itself becomes encased in volcanic ash after a volcanic event. The ash cools and hardens into a stone that we call pumice, right? And you guys might be familiar with what pumice is. So they sell pumice stones at the pharmacy and at beauty stores to kind of help remove calluses from your feet and things like that. But what it does is it actually preserves the outlines of the bones. It doesn't actually preserve anything inside, right? When we drill down into those kind of what they look like almost casings, is they're hollow on the inside, right? So the bones themselves don't preserve, they become vaporized. And this can create very, very large fossil fields instantaneously, right? Because as that hot ash cloud moves through, it instantaneously kills all the creatures and they become encased in that ash. We also have asphalt tar fossils, which some of you may be familiar. We have tar pits, or one of kind of the largest set of tar pits in the United States at the La Brea tar pits in California. Tar fossils are formed when an organism falls into the tar pit, right? The asphalt turns the bone chemically into a fossil, right? Preserves it. And it can also, interestingly enough, we've noticed, at least at La Brea, it can illuminate predator and prey relationships in the ancient past. We find mammoths that become stuck in this tar pit, and unfortunately, some large predatory cats that take the opportunity to try and kill the mammoth while it's stuck and also become stuck themselves, right? So it illuminates kind of how these large predatory cats would follow these mammoth herds, and whenever they would see an opportunity, they would try to take down a mammoth, right? So there are major tar pits located in both California at La Brea, and also there's a major one located in Trinidad, which is featured here in the photo to the right. And your tar pits really result from subterranean tar deposits oozing to the surface. So this is showing you the culprit himself, the one saber-toothed cat that got stuck in the back of a mammoth and died in the tar pit as well, alongside the mammoth. So as you can see, right, the fossil preservation is actually very well. It does kind of darken the bone over time, but it preserves pretty much almost every aspect of the bone. There's very little decomposition, if any. Ice fossils are kind of a misnomer because they are not actually true fossils, right? They are just very well preserved remains, right? And the remains will actually start to decay very rapidly once temperature changes, right? So they're extraordinarily rare. Most of the time, we only find them in very northern climates or more commonly in mountainous regions. So essentially what happens is the lack of humidity as well as the cold temperatures and the low, kind of degrees of sunlight can basically dry and tan the outside of the organism, right? So the organs on the inside become dehydrated, right? Sometimes they'll actually turn into a dust. But the outside becomes very, very well preserved, as you see in our little Iceman here on the feature to the right, right? So when paleontologists, or more importantly, when the museum specialists get these kind of ice fossils, they have to kind of work on them in a very unique way. What you can see here featured is the ice fossil, but he's actually laid on top of a box which cools and keeps the fossil a certain temperature, right? So that the degradation becomes very slowed, right? In essence, this is an individual that was found, I believe, in the Andes Mountains, and this individual was actually speared through the back, and so they know how he died. And what they're doing there is they're trying to open him up from the front to try and extract the spear point that is sticking out of his back. So unfortunately, we don't really find fossils like this, right? The preservation is not that well, right? But we do find very, very, very well preserved mammoths like our little Layuba, which we'll see here in just a second. So this is an ancient baby mastodon that's a little over 30,000 years old, and as you can see, it's got near perfect preservation, right? We don't see a whole lot of the fur. There's not so much fur left. We do have another instance of a mammoth named Layuba that comes to the Cleveland Museum of Natural History every once in a while. And that one actually has even better preservation than the specimen we're looking at now. That one has the fur and everything is intact with that. So sedimentary fossils, we kind of already discussed these a little bit. They're formed by an organism becoming buried in lake or stream sediments, right? And they are formed under large amounts of pressure. Most often we find marine organisms that are fossilized as opposed to land-dwelling organisms. And they're usually found in fossil beds, right? And they're contained within sedimentary stone. So essentially you find something like this here, and you would have to extract a big block of stone here and slowly work on extracting each of the individual fossils from it. So fossils do not stop at just simply a fossilized piece of bone or a fossilized creature, right? We also have geologic stones, basically, that are made out of fossilized creatures, right? You have a fossiliferous limestone, which is featured over here in the top right. You have a coal is actually fossilized creatures, right? Is it's essentially what happens when plants decay and become pressurized under large degrees of pressure and heat. They transform into coal over time. You also have peat bog moss down here in the bottom left that will turn into fossils, right? As well as you'll have a conglomeration of fossilized stone that are fossilized shell creatures that'll come together. So if we look at peat bog fossils, right, what we're looking at here in the picture is actually peat bog material that becomes fossilized and they dig up and kind of pile up. So it's similar to tar in that the creature becomes entrapped within the peat bog. It's similar to ice in that it does not fossilize. Once you remove those creatures or those kind of dead organisms from the peat bog, they'll begin to deteriorate pretty quickly. The peat bog burials are extremely common in places in Europe. We'll look at a few of them. And what essentially happens is there's so many tannins from the rotting vegetable material, essentially, or plant material in the bog that all of those tannins will kind of naturally embalm the bodies or the organisms that die, and their remains end up in the peat bog itself. So peat itself will fossilize after about 1,000,000 years, and this is what you're looking at in the picture to the right. So here's one of our Northern European peat bog fossils. As you can see, it's not really a fossil, it's just a very, very well preserved piece of human remains. So preserved, in fact, that you still have the kind of red hair on the top there. And you can see this individual actually died from a broken neck. And more importantly, if you look at the kind of posture that he has here on his arms there, this individual was actually bound with his hands behind his back. So this was not a kind of natural death or a death by accident, right? This was either a ritual murder or a plain old-fashioned murder, right? Here's another example of those peat bog fossils that they find in Europe. This individual, as you can see, did not have the most pleasant of deaths. So you can see that he's got a rope that was bound around his neck. So you can even see that the rope itself, which is, textile materials, very rarely preserved, right? We very rarely find textile materials even from 200 years ago. So these individuals are about 4,000 or 5,000 years old. And you can see the individual, it was basically, when he died, he was just kind of tossed into the peat bog itself. So the next few slides, we're going to go over what we call different dating methodologies, right? We'll look at kind of more chemical dating, and then we'll look at something called relative methods of dating. One of the first ones we'll look at here is something called stratigraphic correlation, right? So the relative age is determined by comparing the incidence of one event to another, right? So in essence, those incidents you're looking at are the different layers of Earth, right? And we all know, based on the law of superposition, that those at the bottom of the stratum are older than those at the top, right? So the layers at the bottom are older than the layers at the top. So stratigraphic correlation matches up strata based on a criterion to place the scale of time in a large region, right? So if we know how old a layer of rock is, we know that if we find a fossil above that layer, it's going to be younger. And if we find a fossil below that layer, it's going to be older, right? And if we have a fossil that cuts through multiple layers, we know that it's going to be younger than all of those layers, right? So this image here shows you just when we're kind of digging in various places, right? This is actually showing you a cave site. You can actually outline the different stratigraphic layers of soil, right? So if we're able to chemically date the elements within each of those layers of soil, we can determine how old any organism is that we find or any artifact is that we find in each individual layer. In terms of chemical dating, we have a few different methods. One that we talk about, or one that's used an awful lot, is something called fluorine dating. It's used to measure levels of fluorine in bones to determine the relative age, right? Later on in the semester, we're going to talk about something called the Piltdown skull. There was a huge controversy around the turn of the 20th century about whether or not there was an ancient human ancestor in England based off of the remains of that were found in a place called Piltdown. In essence, it turned out after dating it multiple times, a guy named Kenneth Oakley from the British Museum determined that it was a forgery, right? Based on the fluorine dating, he realized that it could not possibly be as old as they were claiming. But we'll get into that in much more detail in one of the later recorded lectures. In terms of chemical dating, we also use strontium dating and carbon isotopes. As a matter of fact, strontium can even be used to geographically orient a specimen. If I have a piece of human remains, particularly the teeth, I can use strontium to determine where that person came from on Earth, because each kind of region of the planet has different strontium levels, and those strontium levels become incorporated into the plants and the animals that you eat, and thus become incorporated into you, right? So based on those strontium levels, they'll match up to different geographic regions. Carbon isotopes can be used. Essentially, you're measuring the variation between, or the kind of ratio between how many carbon and decayed carbon isotopes that you have, but we'll talk about that in a little more detail here in a second. So here is showing you kind of the process of how fluorine works, right? You have, if you look at the image, you have the different strata and it matches up to the amount of fluorine, right? So as you move further on in time or further back in time, you have the fluorine will increase, right? So if you're looking at high levels of fluorine in the bone, you know that it's much older, right? If you're looking at very low levels of fluorine, it'll be very, very recent. Looks like I misspoke earlier. I guess we're going to talk about Piltdown Man now. It was discovered by Charles Dawson in 1912 in Sussex, England. It was thought to originally be a missing link between ape and man. Fooled experts for over 40 years, right? And it gave England an ancient human fossil, right? And that's why Charles Dawson, as well as some of the other kind of experts of the time, fought so vehemently to hold on to the idea, even after Kenneth Oakley debunked it in 1953, right? Because England wanted to have an ancient human fossil, to have, prove the antiquity of humans in England, right? To kind of bolster their imperialism at the time. So this is just showing you on the left here, we have Charles Dawson, who, as a matter of fact, was going through a large bankruptcy at the time that he found the Piltdown skull, which is probably part of the explanation for why he forged it. Then you have Woodward here in the middle. He was the original researcher that Dawson took his materials to verify that it was an ancient human ancestor that they were looking at. And then on the very, very right here, you have Kenneth Oakley, who ran the original fluorine testing that debunked the Piltdown skull. So this is showing you the Piltdown skull here on the left versus an actual ancient human skull from around the same time period that they were claiming the Piltdown skull came from. And you can see there's clearly some huge differences. Yes, there's a bit of a difference in the brain case, but the primary difference that we see is if you look down at the jaw structure of our Piltdown skull here, you notice that the teeth look a little strange, right? They actually look like they have a slightly different shape, and the canines themselves have a slightly different shape than a human does. So what we're looking at here is somebody who took a orangutan jaw and tried to place it on an old human skull. So in essence, if you look at the TMJ, or the temporal mandibular joint region, it's missing, and that's because that region never matched up. If you were to actually reconstruct that region and place it on there in its correct orientation, the jaw would not match up with the rest of the skull. So when you look at the kind of Piltdown skull overall, you have some chimpanzee teeth contained in there. You also have a 500-year-old human skull. That's kind of the top part of the skull. And then you have a 10-year-old orangutan jaw that had been doctored to look like it was ancient. They went so far as to actually paint it to make sure that it looked old. So there are more or other relative methods for dating a fossil. We use something called biostratigraphic dating, or faunal dating. And this compares different fossil forms based on the first appearance of the organism through its extinction, and assumes a relatively constant rate of reproduction. So in essence, this particular method is not particularly very precise. So we would really prefer to use some sort of chemical or geologic dating methods, because these can, when you use biostratigraphic faunal dating, it can go over vast expanses of time, that, there could be vast amounts of morphological change that you may be missing because you're just simply kind of looking at its first and last occurrence in the fossil record. So we also use something called cultural dating, which is what we refer to as typology, or in archaeology we call it seriation. Cultural dating uses changes in material cultures, right, such as stone tools, to establish a chronology, right? So we know that Oldowan tools are our earliest tools based on chemical dating, and we know that our Acheulean tools come later. So we can if we find fossils in the same layer with Oldowan tools, we know that they have to be from around the same time period that Oldowan tools were being made, and vice versa with Acheulean. If we find Acheulean tools in the same layer with a fossil, we know that that particular creature was living around the same time that they were making Acheulean tools. This is showing you a kind of the more sophisticated tool type that comes later after Acheulean tools. It's something that we call Paleolithic tool type. This one's made with something called the Levallois technique, which is where they take large, broad flakes out of the sides of the arrowhead. You can kind of see the big channels that are created by that, and they continue to do that until it gets it down to a kind of razor sharp edge on each side. So we already talked about kind of relative methods of dating. That's where you're using kind of a piece of evidence or kind of a broad pattern in order to date the fossil specimen you're looking at. So let's look at some absolute dating methods, which these always result in a numerical date, right, such as 252 years BC or 3.1 million years BP. And the older dates are often given with a margin of error symbol such as 5.3 plus or minus 0.4 million years, right? And that's because when you start to get further back in time, the older a specimen is, the more difficult it becomes to use chemicals, or the more degraded the chemicals are that you're using to date that particular item. So based on that last slide that you saw of those bristlecone pine trees that can live up to 5,000 years, they are what allow us to kind of use this method or this procedure called dendrochronology, right? It's kind of halfway between a relative versus an absolute dating technique, because you can actually derive a number from it. And essentially what this is saying, or the logic behind this, is that trees grow at a fairly constant rate. And essentially you can count the tree rings inside of the tree and determine how old that tree was when it first started growing, right? And if you find objects that are near the tree, or you find a building made with one of the trees, you can determine when about that building may have been made. You also can use dendrochronology to determine weather patterns in the past. Depending on how thick or how thin the ring is, will actually tell you the amount of rain. In very, very plentiful years, the outer bark or the outer kind of shell is a little bit thinner, and very, very kind of very plentiful years, it's thicker, and then kind of scarce years, the layers become very thin, right? So you can actually kind of gauge the health of the tree over time. When we look at carbon isotope dating, what we're looking at is kind of how carbon-14 is a kind of radioactive isotope that occurs, right? So essentially, carbon-14 is produced in the atmosphere. It oxidizes and forms carbon dioxide, right? That C14CO2 is used by plants in photosynthesis to produce food, right? And then it becomes incorporated into the plant tissues, right? Most of the CO2 or carbon-14 is also absorbed by the oceans, right? Animals consume those plants and those creatures from the ocean, which contain a lot of carbon-14. And then when they die, that carbon-14 starts to become converted, right? And what we're really looking at is the decay rate of carbon-14. What I want you guys to know, though, is that most carbon that naturally occurs is carbon-12, right? So we know that when we're looking at carbon-14, we're looking at something that we can definitively date. So your carbon isotope, or otherwise known as your radiocarbon dating, is accurate to about 50,000 years before present. This is useful in dating anything that was once alive, such as animals or their hides, their bones, plants, and the textiles that are made from plant fibers, things like charcoal, as well as seashells, right? The half-life of carbon-14 is 5,730 plus or minus 4 years, right? So what you're looking at is really how much carbon-14 do you still have left in the specimen that you're looking at. Another form of absolute dating that's used in paleontology is carbon-argon dating, or excuse me, potassium-argon dating. It dates volcanic rocks above and below fossil layers, right? It can date things that are older than 200,000 years. And this is because radioactive potassium has a much longer half-life than radioactive carbon, right? So essentially what we're really doing is we're measuring the decay rates of these specific molecules, right, like carbon or potassium. We also have an absolute dating method called fission track dating. It looks at associated rock crystals that are contained within geologic formations. And when uranium decays, it leaves a mark on that crystal. And this only really works for the last few million years. In the image I'm about to show you, you're going to see kind of what those marks look like. And what you're doing is essentially measuring how long those marks are. And how long the marks are will tell you how old that particular crystal is that you're looking at. And the last absolute dating method and the end of our presentation here that we'll look at is amino acid dating, right? This measures how polarized light bends around amino acids, right? If it bends to the left, you have more L isomers. If the light bends to the right, you have more D isomers present in the organism. So it measures the level of D isomers present. The longer the organism has been dead, the greater the D isomers, right? So essentially you're taking these amino acids that you find, which if you find any, because remember amino acids are a biological material and may not preserve very well. So if you find them, you can use polarized light to determine how old the specimen is based on its reaction with those amino acids.